91.1%. Just let that number sink in for a second. This isn't a passing grade on some middle school pop quiz. That is the staggering accuracy score achieved by an AI on the USMLE MedQA benchmark. The United States Medical Licensing Examination. 91.1%. We are officially so far beyond the era of simple AI writing assistants and basic chatbots. Which brings us to the massive question anchoring this entire explainer today. Is AI actually ready to become our primary scientific research partner? Because, look, it's one thing for an AI to, say, write a polite email, but it is an entirely different universe for it to tackle the complex, multi-hop reasoning required in the hard sciences. The AI science revolution from medicine to math. Welcome to the Explainer. I am so incredibly thrilled you're here. Today, we're taking a focused, domain-by-domain tour through some absolute breakthroughs in recent AI research. We're going to look under the hood of the Gemini models and see exactly how they're pushing the very boundaries of what machine intelligence can do in science. Section 1. Breakthroughs in Modern Medicine, the MedGemini Frontier. Okay, let's dive right into this. Medicine requires an incredibly complex mix of reasoning and, up-to-the-minute clinical knowledge. It's notoriously difficult for AI because it demands the ability to process what we call multimodal data, so meaning text, images, videos, and charts all at the exact same time. To see how AI is actually handling this, let's map out MedGemini's DNA. It doesn't just start from scratch, right? It inherits its core strengths from the base Gemini models. We're talking advanced reasoning, multimodal understanding, and long context processing. But then it undergoes serious medical specialization. It's fine-tuned with customized encoders and self-trained with web search integration. The result? Massive benchmark improvements across the board, completely outperforming prior state-of-the-art models. So how did it actually pull off that mind-blowing 91.1% on the medical exam? Well, the secret sauce is this uncertainty-guided search loop. Instead of just blind guessing, the AI acts a lot like a careful human researcher, double-checking their own work. Step 1, it generates multiple possible answers using a chain of thought process. Step 2, it looks back at its own answers to identify any conflicts or uncertainties. And step 3, if it's not totally confident, it actually generates its own search queries to resolve those conflicts before giving a final answer. It literally knows when it doesn't know, and it actively goes out to find the facts. Now, that's text and data. But let's push the boundaries a bit. How does an AI actually see a surgery? We know these models are multimodal, sure, but I really want you to imagine feeding a live, highly complex medical procedure video directly into a neural network. Think about the kind of dialogue happening in this scenario. The AI is analyzing a video of a laparoscopic cholecystectomy, basically a gallbladder removal from the Charlie-Cady dataset. And it doesn't just, name the tools like the grasper and electrocautery hook. When asked how to avoid injuring the bile duct, the AI advises the student on the critical view of safety, explicitly explaining how to dissect and clear Calote's triangle. It's having a nuanced, totally context-aware dialogue about a surgical video. Section 2, Mastering Math and Biology, Proving the Unproven. Let's see how this builds when we shift gears from applied medicine over to the theoretical sciences. Because if you really want to test a model's logic, you give it rigorous mathematics. Take this elegant equation. In a recent case study, researchers were totally stuck on a complex discrete recurrence problem. They prompted Gemini, and the model didn't just blindly crunch numbers. It actually proposed this explicit closed-form candidate, r of k comma k equals 2 minus the square root of 2, and then it delivered a complete proof by induction. It provided the exact missing technical ingredient that the researchers desperately needed. And it absolutely did not take shortcuts. The AI took highly complex, deliberate steps. It mapped out the algorithm's case analysis to the specific AKH, BKH, and CKH parameters. It identified a specific global T inequality that needed replacing, and it pinpointed the exact monotonicity relation along the diagonal to make the whole proof work. This is sophisticated, high-level mathematical deduction happening right before our eyes. And that same logical rigor applies perfectly to biology too. The MedHub QA challenge requires connecting totally separate, disparate pieces of biomedical information. By using advanced prompting, basically structuring the prompt like a scientific dialogue with explicit chain-of-thought examples, The concept level score for Gemini Flash jumped from a baseline of 0.565 all the way up to 0.720. That is a massive leap in reasoning, just by changing how we talk to the model.
Section 3. Pushing the technical frontier. How is it actually learning?
Okay, so we've seen it ace medical boards, analyze surgery, and prove complex math theorems. But as a focused learner, you're probably asking yourself, how is it actually doing this? Let's peel back the curtain for a second. The absolutely crucial shift here is moving from few-shot to many-shot learning. In the AI old days, you'd give a model maybe 3 or 4 examples in its prompt, few-shot, right? But with massive context windows handling millions of tokens, we are now firmly in the many-shot regime. We can feed the model hundreds or even thousands of examples right at inference time. This allows the AI to actually override its own pre-training biases and learn highly complex, high-dimensional functions on the fly, without ever needing its core weights updated.
But how do you rigorously test if an AI can really plan ahead and learn in a dynamic environment? Well, you have it play Pokémon. Seriously, I am entirely serious. To test Gemini 2.5 Pro's new agentic capabilities, basically its ability to take actions over a long time horizon, researchers unleashed it into the classic video game world with Squirtle here. Following this timeline of gaming milestones, the AI didn't just mash buttons randomly. It successfully navigated the map, entering Verdian Forest, beating the gym leader for the Boulder Badge, navigating its way out of Mount Moon, and playing all the way to the Thunder Badge over hundreds of hours of simulated time. This brilliantly illustrates how the model can execute long horizon reasoning, remember its past actions, and actually plan for the future in a highly complex environment.
Section 4. The future of discovery. Autonomous agents. So let's tie all of these threads together. You take the medical and biological analysis, you add the rigorous mathematical logic, and then you combine it with that long horizon, Pokemon-playing agentic planning. What do you get? You get deep research, powered by Gemini 2.0 Flash Thinking. This is not just a search engine. This is an autonomous agent that on your behalf plans a strategy, searches the web, analyzes the information, resolves conflicts, and synthesizes comprehensive multi-page reports on highly complex topics in just minutes. It's applying the exact same systematic reasoning we saw in the Med Gemini loop, but making it accessible for literally any complex project. However, we do have to stay grounded here. As this quote straight from the researchers highlights, we absolutely must acknowledge the role of AI systems as assistive tools for expert clinicians and conduct rigorous validation before real-world deployments. Look, no matter how incredible these advancements are, these models are currently powerful assistants, not replacements. In safety-critical domains like medicine, human oversight and rigorous validation are absolutely non-negotiable. But I want to leave you with this final, really provocative thought. If an AI can already prove mathematical theorems that stumped researchers, if it can digest millions of medical records in an instant, and if it can autonomously plan and execute deep research, what does the next decade of the scientific method actually look like? Human discovery is fundamentally changing right in front of us, and we're just at the very, very beginning of understanding what our new AI research partners are truly capable of. Thank you so much for joining me on this explainer, and keep learning.